Okay. So introduction. The goal today will be to explain competing particle systems, which has been introduced by Ioannis and Tomoyuki a few years ago, which is a degenerate model with free particles. So I will explain later on how to define it, but you see the picture of a process here, so it's really special. And I will focus on what is called the gap process, which is the process of the distance between two particles. And in fact, this gap process will behave just as a reflected Brownian motion, but a degenerate reflected Brownian motion. And so the goal will be to find the invariant measure of this process, of this gap process. To do so, I will have some functional equation that I have written here. And the kernel of this functional equation will be here. And you see the degeneracy come from the x minus y square. This is the degeneracy. And I will have some tools to study it, some complex analysis with boundary value problems, some combinatorics. I will explain you what is a Tut's invariance. Some Galois theory, I will not emphasize on it, but it's something important also. And the compensation approach that Maxence presented yesterday, I don't know if I will have time to tell a word about it. So the second aim of the talk is to generalize some parameters introduced by Varadhan and Williams a few years ago, which is called alpha, and maybe you know it, which depends of the angles of reflection, epsilon and delta, and the angle of a cone. And a lot of properties depend on the value of this parameter. Recently, with some other co-authors, we also introduced two other parameters in the non-degenerate case, which we called alpha 1 and alpha 2. And some properties depend also on the value of alpha 1 and alpha 2. And so today, I'm going to explain you how to define a new key parameter, which we call gamma, in the degenerate case this time, for degenerate Brownian motion, reflected Brownian motion, which will be, in some sense, the analogous of alpha, but in the degenerate case. And so we'll also have two other parameters, gamma 1 and gamma 2. I will not emphasize on it. In fact, if I would be more precise, the real thing I should maybe have written, alpha corresponds to a minus gamma plus 1. It just depends on the convention, but it's more this. OK, so you don't have to see all the slide here. It's just for you to understand that here you have alpha. And if alpha takes some values, there are some properties which are satisfied or not satisfied by the reflected Brownian motion. And here is some work that we have done, which also says that the nature of the Laplace transform depends also on the value of alpha. And so the goal today will be to, make the same pictures, but in the degenerate case, for gamma, in the degenerate reflected Brownian motion. So this is an ongoing work and for future work, so nothing will be finished, but I will present it to you. OK, so this is my plan. First of all, I will present the process. I'll try to explain how it's defined. Secondly, I will show you the main results that we obtain about the invariant measure of gaps. And finally, I will explain you the proof with the analytic approach that we developed. So competing particle system, what is a rank-based diffusion and what are asymmetric collisions? So I will say a bit on this slide for you to understand. So let's take X, a process, an n-dimensional diffusion, described by this equation. So what is it? Delta K is a drift, and sigma K is a variance. And what is important to understand is that the drift, it depends on the rank of the particle XE. This means that if X is the higher particle, the drift will be equal to sigma 1. But if the XA is the second particle, the drift will be equal to sigma 2. Delta 2. So in blue, there is a color code, if you have understood. In blue, it's what I call the process by name. So I is the name of the particle. And in red is the process by rank. K is the rank of the particle. And so R1, Rn is the ranked process. So R1 is the highest particle, and Rn is the lowest particle. And so we can describe some process where the drift and the covariance depend on the rank. And I will not focus on it, but we consider the non-stickiness condition. That means that there is no time when two particles collide. The time is 0. So I hope it's clear for everyone. And so this is just a picture. Thank you, Tomoyuki. I take this picture from your slides. So you see the ranked process, for example, with some value of a drift and some value of covariance. So I don't know very well the literature, but I just made this slide to tell you that a lot of works have been done of this kind of process. A lot of smart people studied this process. The limiting particle density when the number of particles goes to infinity, for example, is described by the Maclean-Vaslov's equation. And of course, there are some applications to financial markets. So I won't detail, but if you want some references, there are a lot of on this model. And to begin, I'm going to focus on the non-degenerate case. What I call non-degenerate case is when sigma chi, it means the variance, is positive. So when the variance is positive, all of them, yeah, for all k, is positive. So in this case, there are a lot of works which show that there is existence of weak solution, uniqueness distribution, pathway uniqueness, etc. You also have positive recurrence property, which will interest us because we will study the invariant measure. And we also have some strong solution and the triple collision, which are studied. So there are a lot of works. And I will focus on something. So here, I just rewrote the equation that you saw before. So this is the drift and the sigma k, which depend on the rank. And Banner and Gomrazny have written a formula. So Ioannis just told me that in fact you can avoid, you do not have to assume this no triple collision. Here it's the process by name, and here is the process by rank. So if you want to write the process by rank, it's just a drift, delta k, which depends on the rank. So it's just a simple drift, of course. And it's just a simple covariance times a Brownian motion, because the covariance depends only on the rank. But you could say, it's finished because it just depends on the rank. But no, you have to add some local time, which are the local time of the collision between two particles. So it's kind of pushing process, which makes that the particle cannot cross. And so they are reflected against each other. So you have to add this local time, you see, between the two particles. When this is 0, it means that two particles collide. And you see the 1/2/2, I will, in the next slide, I will explain. So it's the same equation here. You see the rank process, Rk, the drift plus the Brownian motion plus the local time, which are in fact symmetric. Why? Because they are equally divided between two particles. If you want a pushing process, if you do not want that the two particles cross, you have to add the local time. And so you can choose either you give 1/2 and 1/2 on the local time of the two particles, but you also can define a process with asymmetric collision. So it will be the same formula, but instead of 1/2 here, you will have some parameters, qk and qk minus, which are positive numbers. In fact, you do not have to assume it is positive, I believe, which satisfy this equation in order to have one invariant, one local time. Yeah. We can define another process. I have not done it, but process by name with local time, which gives some asymmetric collision. It's a work of Ioannis. He will. Okay, okay. Yeah, you will. I don't know, but yeah, if I give you the red part, you can obtain the blue part, but you no. You get 1/2 in the case that I presented before, just when, yeah, it's a most simple case, yeah. Yeah, and I haven't presented in detail the asymmetric collision, but because I will be interested only in the ranked process and not in the process by name for asymmetric collision. Yeah. Yeah. So sorry, I'm a bit fast. It's not my part in some sense, but yeah, I hope you get the main idea of this kind of process. And so this is done in a work of Characterise, Pal, and Skolnikov. Okay, so I am interested in the gap process. What is the gap process? The gap process is the distance between two ranked particles. So define Z1, Zn minus 1, the gap process like this. And so the gap process, in fact, will behave just as a reflected Brownian motion in the orthant, the same reflected Brownian motion that Harrison, Rayman, Williams, etc. defined many years ago. And so if you take the equation of the previous slide and you replace it in this formula, you get this equation. And so it gives you this drift, which delta 1 minus delta 2, this covariance matrix, and this reflection matrix with one, because it's I minus Q, so with one in the diagonal and minus Q on the two line here. And so you get an oblique reflected Brownian motion, which depends on the reflection parameters Q. So this is the main object that I'm going to study. But this is in the non-degenerate case. So just to make it simple, in 3 dimensions, because we will focus on 3 dimensions, it gives this process. So you have here the reflection matrix, the covariance matrix, and it will give a reflected Brownian motion. For symmetric collision, you will have the reflection vectors, which will be like this in the symmetric case. And now I'm going to focus on the degenerate case, which means that one or more of the sigma k are equal to 0. So there are some works with 2 particles. And recently, 2 years ago, Ioannis and Tomoyuki made a work for 3 particles. And they studied 2 cases. First case is when the 2 extremal particles are ballistic, which means like sigma k are equal to 0, and the not cases where it's the middle particle, where sigma k is equal to 0. And today we will focus on the first case, which is that sigma 1 equals sigma 3 equals 0 and sigma 2 equals 1. We could take another value. We just take 1 to make it simple in the formula, but it doesn't change anything. And so we will study this process. So here I just put a picture for you to understand. So this is the process by name. You see that the color change. And this is the process by rank. The red is always in the center, the green is below, etc. So you see well the process by name here and the process by rank here. Okay. And we are going to study this process And so if you take a degenerate competing three-particle system, if you study the gap process, which is the distance between two particles, it will give you a degenerate reflected Brownian motion, which have this path. Okay, so we want to study this process, which is a degenerate reflected Brownian motion. So I change a bit the notation to make it simpler. So Z1, Z2 is the two-dimensional reflected Brownian motion. mu1, mu2 is the drift. Here you have a degeneracy. So this is the same Brownian motion. There is -1 plus. The degeneracy, you can see it in this covariance matrix where the determinant is 0. And here you have the reflection vectors, R1 and R2. In the symmetric case, it is to -1/2. And there is an existence condition that is similar to what is done for SRBM. We will assume this condition. Okay. And you also have a recurrence condition on this process, which is also the same that Hobson and Rogers did a few years ago for a non-degenerate process. So what is the recurrence condition? In fact, it's a competition between the drift and the reflection vectors. So I have no time to explain too much, but you have to make that the reflection vector are not too inclined towards infinity in order the process doesn't go to infinity along one axis, or you do not want the drift to be positive and you have some, and so this is this condition that we will assume along this talk. So the main goal now is to study the invariant measure and more precisely the Laplace transform of the invariant measure that we define here. And we also define the Laplace transform of the boundary pi1 and hat pi1 and hat pi2. So these are our unknown. We want to find pi, okay? And there are some partial differential equations which characterize this invariant measure. So it's quite classic, so it's a bit quick if you haven't seen before, but you have this equation which characterizes the stationary distribution inside the quadrant, and you have some boundary conditions which are some condition on the derivative on the boundary. And in fact, this PDE, if you take a weak version of this PDE, you obtain what is called in the literature the basic adjoint relationship, which is just in some sense a weak version of these things. And you just integrate this partial differential equation against a test function, which is bounded, C2. And in some sense, this equation almost characterizes the invariant measure. So we want to solve this equation. So if you haven't never seen this equation, it's just if you have, for example, a Markov chain, you want to find the invariant measure, you just have to solve the equation pp is equal to pi. It's just the same equation, but more complicated. Okay. And now, if you take an exponential function for the test function, it's not exactly allowed but you can do it. You get some functional equation that I told you before, which is like this. You have a kernel here, and here you have what happens on the boundary. So some polynomials of degree 1 of two variables. And so I emphasize that the degeneracy comes from x minus y squared. This is the degeneracy. It comes from here. So the goal now is to solve this equation. And in fact, I have done all the probability here. Now we are going to do some analysis and algebra, but in some sense, the probability are almost finished. Okay. So I finished my first part, and now I'm going to present the main results before to explain you how to find it, if there is no question. Okay. So first main result in the symmetric case. In the symmetric case, I will assume normalization to make the formula more pretty, but you are not you can remove this hypothesis and everything works. But along all my talk, I will assume that, but it's not necessary. So we are able to compute the Laplace transform, which is equal to this, in some sense, simple formula, a polynomial of degree 3 divided by cosinus and the square roots. And we are able to invert this Laplace transform and to obtain the density of the invariant measure. So this is on the boundary. So you see it's a complicated sum of exponential, infinite sum of exponential with a polynomial here of degree 6, 7 or 8. And here you have a quadratic, something quadratic here. So this is our first result. It's not obvious at all. And in fact, we also can obtain some more general results for the bivalent density. So here you have a picture of density. So we get it really explicitly. We have the shape of it. And it's an infinite sum, just as Maxence presented yesterday. But you will understand why I have written two sums. I will explain it at the end of the talk, of exponential. So the AN, BN are some quadratic polynomials in n, and the Cn are some complicated polynomials of degree 8. Okay, so this is in the symmetric case. Okay, in the asymmetric case, it's a bit more complicated. So it's an ongoing work with asymmetric collision. We have a similar formula, but the Cn will be more complicated. There will not be polynomials, and you will have some asymptotics. The Cn will be equivalent to n to this, and gamma is what I defined at the beginning of the talk, is the equivalent of alpha that I was talking about. So this is for asymmetric collision, and now I present you the result for the asymmetric collision. So the gamma will be crucial for asymmetric collision, and so this is the parameter which is reminiscent of the alpha parameter. And I will have several results. So for example, if gamma is a positive integer, the Laplace, the invariant measure, the density of the invariant measure will just be a finite sum of exponential. And the n will be equal to gamma. So this is really simple and really beautiful. And for example, there are skew elastic collisions for gamma equal 1. It has been done by Ioannis and Tomoyuki in their paper. You just get one exponential. But if you take gamma bigger, but integer, you will have a sum of exponential.
Perhaps important to say at this point, practically everything we know up to now has been exponential or products with exponential.
Yeah.
Making baby steps towards it.
Yeah. We start with this and then we. And so in the previous slide, I had gamma a positive integer. Now I'm going to look at gamma a negative integer. And when gamma is a negative integer, you will have this formula for the Laplace transform. It will be equal to a polynomial of degree n, with n is equal to minus gamma, divided by this function, this cosinus, and this square root. And we are able to inverse this Laplace transform. And miraculously, when you inverse the Laplace transform, we obtain some Jacoba theta type function. And you have to apply some differential operator to this theta type function. So if you want to see the result in a more simple case, which is in the symmetric collisions, for symmetric collision, you have R1 is equal to R2 is equal to minus 1 over 2. And if you make the computation, you obtain gamma is equal to minus 3. And so you have here the explicit formula for the Laplace transform on the boundary. And it's so really everything is explicit. And now, sorry, it's my last slide for the main results. We get also something a bit more, not complicated, but I don't know if you are used of it. It's something that the combinatoricians loves, is to classify the Laplace transform in terms of some hierarchy of function. So maybe you all know the rational function. Maybe you know also what is an algebraic function. And you can also define what is a differentially finite function and a differentially algebraic function. So definite function is a function which satisfies a linear differential equation with polynomial coefficients. And the same for algebraic, but it's a polynomial differential equation. And in so this classification, this hierarchy of function is useful. I cannot explain in detail, but for example, if you know that the Laplace transform is rational, it will give you that the density is the sum of exponential, because we will invert the Laplace transform and it will give the sum of exponential. And you have also some properties, is that if Laplace transform is definite or differentially algebraic, it will give you some recurrence relation for the moment of the density. So you will obtain some algorithm which compute explicitly all the moment of the density, and so you will know very well your density. So it's just for you to understand why this result is interesting. And so currently with Jules Flin and Thomas Dreyfus, which is a specialist of difference Galois theory, that's why I'm doing this paper with him, we are classifying the nature of the Laplace transform. So you see this ongoing work. We have not finished, so I cannot tell you what are the results, but we are sure that it will depend on gamma, gamma 1, and gamma 2. And we just have, for example, for now, the rational case and the differentially algebraic case. Okay, so I hope I have not lost you with this slide, but you can ask if there is some problem, but it's not crucial for the talk. Okay, so now I'm going to present the proof. I will start slowly to present the analytic approach. Okay, so the method, in fact, here that I will employ is a mix of two methods. The first method is an analytic approach developed by Fayol, Yazgonorodsky, and Malishev. They published this little yellow book. It's about random walks. And in fact, what Kilian did, Irina did, and then me in my PhD thesis is to apply this method to the continuous case for Brownian motion. And the second approach is a Tut's invariant approach. Tut's developed a method to enumerate some colored triangulation. And so he developed some approach based on some invariant. I will explain you what are these invariants. And we mix these two methods and we'll obtain our results. So what are these methods? First of all, this is the kernel functional equation. It's just matter of convention. I just changed here the kernel, but believe me, it's the good kernel. We will assume this hypothesis that we can remove, but we'll assume this. So the first thing to do when you have a kernel functional equation is to study the kernel. Study the kernel. When you heard the word kernel, you have to cancel the kernel. It's just a reflex. So to cancel the kernel, it gives you some Riemann surface, which is the point which cancel the kernel. And you can parameterize this Riemann surface. So the definition of the Riemann surface is here. So you see just the complex points which cancel the kernel. And you can parameterize this Riemann surface really simply by this equation. It's just a polynomial of degree 2. And so you see that k of x of s and y of s is equal to 0. You can replace it. You do a computation and it works. So it's a really simple and really beautiful parameterization, which works because we are in the degenerate case. Of course, if not, it would be a bit more complicated, but it would also work. So remember this parameterization. And now I'm going to explain you what's some involution on the Riemann surface. So this is the parameterization. And I will define zeta, which is equal to minus s minus mu2. And eta is equal to minus s plus mu1. So it's easy to see that if you compute x of minus s minus mu2, it will be equal to x of s. You see, the formula is simple. So, and the same for y with eta. So in fact, x is invariant by zeta and y is invariant by eta. You see? And eta and zeta are involution, which means that zeta square is equal to identity and eta square is equal to identity. And if you make eta zeta, you get some translation, s plus 1. The 1 comes from the fact that mu1 plus mu2 is equal to 1. Okay. So it's some small computation, but it will be important for the next of the talk. So I can show you what these involutions look like geometrically. So the parabola here is the real part of the Riemann surface. So it's just the real points which cancel the kernel. It's just a parabola because it's a degenerate kernel. if it were not degenerate, you would have obtained an ellipse. I think maybe you. And so zeta is just the automorphism to a point here. It will associate this point here. So it has the same x. And eta, to a point here, it associates a point here. It has the same y. Okay? And so it's involution because eta, zeta. So you are coming back. Okay? And so this is automorphism which will act on this parabola. And it will give you some stairs, just as Maxence did yesterday. Okay. So now, thanks to this involution, I'm going to obtain some finite difference equation, which is written here. So it's a really simple equation. It's pi1. It's just the Laplace transform, but I evaluate now everything in y of s and x of s. I want to cancel the kernel, so I take tilde as a convention to when I evaluate in y of s and x of s. And you have, in some sense, pi1 is almost pi1 of s plus 1 is almost equal to pi1 of s, but you have a coefficient here, which is j of s, which depends of k1 and k2, which are the coefficient of which were in the functional equation. This is the parameter of the functional equation. So how do you prove this finite difference equation? In fact, we just have to cancel the kernel, evaluating the functional equation at this point. And so you get at these 2 points on S and in zeta S. So you get 2 equations, one in S and one in zeta S. And now you just have to take care of the invariance by eta and zeta. P2 of zeta S is equal to P2 of S. And P1 of zeta S, you make the invariance is equal to P1 of S plus 1, because you record that eta zeta is equal to S plus 1. And so when you do this, you eliminate pi2 of S, and you get this finite difference equation. And when you get this finite difference equation, there are a lot of theory which tell you how to study this kind of equation. And for example, it's very linked to Galois theory. Okay. So now this equation is beautiful, but we can make it more beautiful. We would have preferred to not have a j, to just have a periodic function, because periodic functions are really simple. So we will try to factorize the function j in some sense to obtain what we call a decoupling function d. So the goal now is to write g as the quotient of d of y of s divided by d of y of s plus 1. Why we want to make it? Want to make it in order to obtain this kind of equation, which is d pi 1 of s plus 1 is equal to d pi 1 of s. Just an equation which will be periodic and more simple to study. And in fact, it is here that the new parameters gamma appear, the parameter which is equivalent of the alpha in the non-degenerate case, because a simple computation shows that this decoupling function exists if and only if the parameters are integers. These parameters are integers. And it's just simple calculus. You can do it on one page. It's not a big theory here. You write it and you got this. And so you can make d explicit. For example, if gamma is positive integer, this is the polynomial for some S1. This is the polynomial which has degree gamma. Okay, that's why the gamma also intervene in the degree. So this is how appears these gamma parameters. And now I just want to focus on the fact to tell you that, in fact, this decoupling function, I should have written d1 because it was for pi 1. You can also obtain a decoupling function d2 for pi 2. And this decoupling function exists if and only if the functional equation admits polynomial solution. So I don't know if you already noticed, but when you study functional equation, there are often polynomial solutions, but often they are not the one you are looking for. So here, when there are decoupling functions, you can find D1 and D2, which are the decoupling function of the previous slide. And you also can find a polynomial of degree of two variables R, which satisfy the polynomial, the functional equation. And so you can prove it using Hilbert's Nullsensatz, which is a bit of algebra, and the fact that the kernel is irreducible. And you can get the equivalence here. So to give you an example, for the symmetric case collision, in fact, we do not have to have all this theory. You can just remark that you have this decoupling identity. And so here is K1, D1, K2. And so you just have to verify this. If you find it, you have, of course, to find it. But if you find this equation, you do not need the theory before, okay? But you find it and you are happy because you find D1, you find D2, and it will give you the solution at the end. Yeah, the miracle has to happen. Yeah, so it's a miracle, and this miracle happens only when gamma is an integer, or gamma 1 and gamma 2 are integer. So how many times? Okay. Perfect. So sorry, there are a lot of definition, but I just defined the decoupling function. Now I'm going to define what is an invariant, because the method is called a Tut's invariant approach, so there are some invariants. So an invariant, it's simple. It's just invariant by the two automorphisms involutions that I have defined before. So I is a function, is an invariant, a meromorphic function, if and only if I is stable by zeta and I is stable by eta. So you remember eta and zeta, the automorphisms. And so if you are invariant, then I of S is equal to I of eta zeta, and eta zeta is S plus 1. So if you are invariant, you are also periodic. Okay, so this is the definition. So now we are going to see if you remember the slide before. So what invariant have we seen before? The question. So the invariant that we have seen before is d pi 1, the decoupling function times the Laplace transform. Because we wanted to have, so I will come before, so we wanted to have this decoupling function to have this invariance, in fact. So this is what I call the unknown invariance. Why unknown? Because we are looking for pi 1. So we don't know this invariance. It's what we are looking for. So this is an unknown invariance. Now I want you to try to find another invariance that you all know. What function, an easy function, satisfies this and this? Do you know a function? So if we simplify the parameters, it is just y of s is just something like, for example, y of s minus and function which satisfy, for example, y of s is equal to y of 2p minus s. I just take some easy parameters to make you understand. Do you know a function which satisfies this? A function which is 2p periodic? Yes, the cosine. So in fact, it's just the cosine. And what we are going to see is that there are not a lot of invariants. In fact, all the invariants are just the cosine function. And the goal now is to express the unknown invariants in terms of a canonical invariance, which I call W, which is just the cosine. Okay? So how to do it? We have some invariant lemma. So I wrote it two versions of the invariant lemma, but which say that if E is an invariant, which is analytic and bounded, then it is constant. So this is the first invariant lemma. And the second invariant lemma, it says that if E is an invariant which has a finite number of poles, which is bounded by a polynomial, then there exists a rational fraction such that the invariant is equal to f of W. W is the cosine. So in fact, you have some lemmas. We say that all the invariants are rational fraction of the cosine, in some sense, with some hypothesis. Okay? And so how do you prove this? It's really simple. It's a bit of complex analysis. I don't want you to you are not obliged to follow this, but you take W, the cosine function, and maybe you know that the cosine function, if you take, so here 0, here P, here you take cos, here you take arc cos, and so here you have C, and this is a conformal function, which means that this is put on this, and so here you have -1, here you have 1, and this correspond to this, and so you have a bijective function which is analytic, and the arc cos is also analytic and bijective from this domain to this domain, and thanks to this, and thanks to the invariant property. So the invariant property here just means that the function here is equal to the function here, and the function here is equal to the function here. So this is zeta, this is eta. So in some sense, the cosinus glues this part and this part on this part, and glues this part and this part on this part. And so you just have to take the invariant times arc cos times W minus 1 to get an analytic bounded function. And you all know that an analytic bounded function is constant by Liouville theorem, or you can get that it's a polynomial, and that's why where the rational fraction appears, you get some polynomials. Okay. So I hope it's clear. The only message is that there are not a lot of invariants, and you can express the unknown invariants in terms of a canonical invariance. So that's how I'm going to be more fast at the end. You can express pi1 in terms of a fractional of f of the cosine divided by the decoupling function d. And that's how we obtain the results that I presented before. So the main results about Laplace transform and differential properties can be obtained like this. And now it just remains to inverse the Laplace transform. So maybe I will not have enough time to finish all the talk, because I will let some question, but just in some easy case, for example, if Laplace transform is 1 divided by a polynomial, it's easy to inverse and to obtain a sum of finite sum of exponential. You just decompose I don't remember the term, but it's easy to inverse this Laplace transform. So this is when gamma is an integer. Now when gamma is a negative integer, you get this formula, which is the polynomial divided by the cosine. This is where the cosine comes from. And the square roots here come from the fact that we had x of s, which is s times something like that. And so if you take s, x is a square root of s. So, okay. And so if you can invert the Laplace transform, I just want you to know that it's linked with some theta function, which is here. And to prove the inverse Laplace transform, we use some Mittag-Leffler expansion, which is you develop the 1 over tangent x. I don't know if you knew this equality. I didn't know before Kilian told me about this equality. So it's an interesting equality. And you can inverse this Laplace transform. Okay. And so now for my last slide, I will be really, really quick because Maxence told it yesterday. So there is also another approach, which is called the compensation approach, which has been developed in the degenerate random walks in the quadrant. And so the goal, in fact, is to compute the stationary distribution without studying the generating function of the Laplace transform. And I will not explain everything in detail because I have no time, but you have to follow this automorphism, eta at zeta, etc. And it gives you some compensation which make this PDE satisfied. And what is different from the talk of yesterday of Maxence is that we have to be careful of the starting point. And the starting point is the intersection between the parabola and the line defined by the boundary condition. And so you have two starting points. And I just want to emphasize that it is not that that this method works only because it's degenerate. So the parabola goes to infinity, and so it converges. If you are not degenerate, you have an ellipse. So you can define this sequel, but it will not converge on the ellipse, and so it will not work. And the second thing is that the positivity is not obvious at all, because the Cn are plus, minus. And so this is what is very complicated. And so you get some solution like this with a Cn equivalent to this, and this is the gamma, the famous gamma, which has alternative sign. And so there is still something that I have not understood, fully understood. You have to adjust with two constants here to make this solution to be positive. And so it's something really delicate, and I have not still understood everything. If someone has some idea on it, go talk to us. So thank you very much for your attention.
Quantum signals are for the 10 minutes. Now 10 minutes for the start.
Okay, so do you know the tail behavior of your stationary measure?
We could know, yeah. Yeah, it's the tail behavior of, yeah, we could know it. Maybe it's what we've done with Maxence in another work. Yeah, but it's another method. You have to use saddle point methods and to get the tail. Yeah.
And what is roughly the answer?
Yes, it is if you know it explicitly. Why do you need asymptotic?
Yeah, yeah, but no, but yeah, you can. So you see, no, this is not this. But it's something like I believe pi of rho theta, if it's the polar coordinates. It's equivalent to, so it depends, but sometimes 1 over square root of rho, I believe, exponential minus some things. And yeah, and it depends on the case.
Is there an analogous theory that would give something in this direction for the parabolic PDE corresponding to the time-dependent distribution?
At the time-dependent distribution, you mean
transient? Yeah, you start with the initial condition.
Yeah, yeah, it's something that we were thinking about with Kilian. We never make it work, but maybe. There is a Kavita.
Let's consider your model with sigma 1 and sigma 3 is 0, and assume that mu1 and mu2 is 0. Is there any relation of this system with a Brownian motion that reflects on it on running maximum and running minimum? Say x of t is w of t plus alpha times maximum of x plus beta times minimum of x.
Sorry, I'm not certain to have understood. So you mean at the beginning?
It's a different system.
Thank you. Thank you for your talk. If I come back to the original rank diffusion problem, okay, so here you studied the case of 3 particles. What do we know, I mean, for the case of a larger number of particles? So in other words, I guess, okay, doing a so nice and precise analysis is probably very far, but what would be left, I mean, from what you have learned here for the 3 particle case to the higher values of n, say?
No, yeah, in fact, if you increase the number of particles, it just as for reflective Brownian motion, it's hard to make the method works, but you have some other colleagues which have studied the case when n is big. So you have some other work. I'm not specialist on it, but for the gaps, it's also reflected, degenerate reflected Brownian motion, yes. But then to study, it's just to the same thing, but to study SRBM in dimension n. So yeah, it's complicated in dimension n.
Well, we only know one miracle there when the basic adjoint relationship forms. I mean, you have two matrices that fight each other, the reflection matrix and the diffusion matrix. They are all loggerheads, except when they decide to make peace. They make peace when the basic adjoint relationship happens, and then the miracle, another miracle. You get the distribution, which is a product of exponents. But that's the only thing. That's what I referred to a moment ago. That's the only thing we want to know.
Okay, Vita.
It'd be nice to know a little more. Here is where we are.
So I think you meant skew symmetry, not the basic adjoint relationship. Yeah, yeah. So the skew symmetry condition, which was done by Williams and Harrison and other people, but yeah, yeah.
Basic adjoint relationship.
Yes, so that's just a general thing, characterization of the stationary distribution. But then, thanks for your nice talk. Is there any case, I mean, you know it explicitly, and do you know when it's just a sum of exponentials with constants and not the polynomials? For example, Decker and Moriarty have this characterization of when they do it in a very different way through reflections to show when you get the stationary. So talking to you beyond the product of exponentials, you also know sum of exponentials for two-dimensional Brownian motion. Do you have any idea when you might get a sum of exponentials?
A sum of exponential? Yes, this you mean?
No, I mean, but it's with a polynomial coefficients.
With polynomial in front of the exponential? No, I have a two. No, I have a two. So look at it. So here it's just some finite sum of exponential. So yeah, I have it when gamma is a positive integer, it's this, and when gamma is a negative integer, it's more complicated. So yeah, so I have the equivalent of Decker and Moriarty. Yeah.
More debate.
You mean the intensity of the drift? Yeah, you say, yeah, I don't know. But your remark is not exactly the same, but if I just can finish on another remark with so just to explain you more geometrically how these parameters can appear. This is the important parameter. In fact, you know that you have alpha is equal to epsilon plus delta minus p over beta. And what is the degenerate case in some sense? The degenerate case is beta goes to 0, in fact. Beta goes to 0, this is the degenerate case. And when beta goes to 0, you have some formula which links epsilon and delta. And when you make it, beta tends to 0, you get minus gamma plus 1. And so, in fact, this is the equation that you can obtain just with some small computation, and you get you find this gamma. So it's not your question, but I wanted to explain a more simple way to obtain this gamma. And so, and also a final thing. So maybe you know that in the non-degenerate case, you have, if this is the invariant measure of polar coordinates, this is equivalent when rho goes to 0, about rho minus alpha and a constant of theta. I think that Ruth show this kind of things in her paper. And so you can show the same thing. This is the non-degenerate, and here in the degenerate case, you show the same thing, but with rho minus gamma plus 1, and this is a constant of theta. So the alpha and the gamma will really be the same in the two model.
Thank you. In the compensation approach, you took the two coordinates of the drift negative?
Yeah.
Okay. So would it be possible to adjust or to have formally explicit sum for the invariant measure in the case of, I don't know, mu1 strictly positive and mu2 negative, but we're still recurrent?
I believe it would be possible. Yeah, just the parabola will be inclined on another.
Okay, but it wouldn't converge.
Good question. You want to push me? Yeah, I don't know. Yeah, we have to think about it.
Okay, thank you.
Yeah, maybe. Yeah, you're right. Good question.